When you picture the end of the universe, you picture a final moment, a last event, the last star going dark, and then the closing of some great book, after which there is no after. We all carry that image, and it feels like simple, common sense. But the strange truth, hiding in our best physics, is that the universe may have no final moment at all. The heat death is not a wall the cosmos slams into. It is a fading that goes on forever, a last page that keeps turning out not to be the last. And it gets stranger, because a finite, dead universe, left alone long enough, does not actually stay dead. By a proven mathematical theorem, given enough time, the cold, dark twitches and order flickers back out of nothing, again and again, without end. So the question is no longer simply how the universe dies. The question is whether it ever truly can. Settle in. Subscribe if this is your first time here, because by the end of this, the silence at the end of everything will not feel nearly as final as it does right now. Let's slowly slip into this. Part 1. The certainty of endings. You already know how this ends. You have known it since you were a child, even if no one ever sat you down and said it out loud. Everything ends. The day ends. The summer ends. The people you love grow old, and then one day they are gone, and the world keeps turning without them. You have watched candles burn down to nothing, and watched fires settle into cold grey ash, and somewhere along the way you absorbed a quiet, unspoken rule about the universe. The rule is that nothing lasts. The rule is that all things, given enough time, come to a close. Notice where that rule actually comes from. It does not come from physics. It comes from a lifetime of watching small, contained things run their course. A fire ends because it runs out of wood. A life ends because a body wears out. A song ends because the composer wrote a last note. In every case, the ending belongs to a thing inside a larger world that keeps going after it. The fire dies, but the room remains. The song ends, but the silence afterward is still part of the same evening. We have never once, in all of human experience, watched the container itself end. We have only ever watched things end inside it. And so when we imagine the universe ending, we are taking a rule we learned from the contents and applying it to the container, without ever checking whether the rule still holds when there is nothing outside to keep going. That single, unchecked leap is the quiet assumption this whole night is built to examine. So when someone tells you that the universe itself will end, you do not flinch. It feels almost obvious. Of course it ends. If the smallest things end, and the largest things we know end, then surely the biggest thing of all, the thing that contains everything else, must end too. The stars will burn out, the lights will go off, and the cosmos will sink into some final, frozen, featureless silence and stay there in the dark forever. There is even a name for it. Physicists call it the heat death, and sometimes they call it the big freeze, and for most of the last century it has been the mainstream scientific expectation for how everything finishes. It is not a dramatic ending. There is no great explosion at the close, no fire that consumes the sky. There is only a long, slow cooling, a gradual draining away of every difference and every motion, until the universe becomes a smooth, cold, empty nothing in which nothing can ever happen again. That is the ending you have been told to expect, and tonight you might think you already understand it. But I want to ask you to do something gentle and a little strange before we go any further. I want you to hold that word, end, up to the light, and really look at it, because it is one of those words we use constantly without ever asking what it means. When you say, the universe will end, what exactly are you imagining? Are you imagining the last star going dark? Are you imagining the last bit of usable energy running out? Or are you imagining time itself, simply stopping, the final tick of the final clock, after which there is no after at all? These are three completely different ideas, and we fold them all into one small word and assume they are the same thing. They are not, and the gap between them is where this whole story lives. Here is something that almost no one believes the first time they hear it. There is a serious possibility, taken seriously by serious physicists, written up in serious journals, and argued about at conferences, that the universe has no end at all. Not that it ends slowly, not that it ends gently, that it does not end. That what looks like the death of everything is not a wall, but a doorway. That the cosmos either repeats itself over and over forever, or that it never actually finishes dying, approaching its own end for all eternity, without ever quite reaching it. There is no end. You probably do not believe that yet. You are not supposed to. Hold on to your disbelief, because we are going to test it, slowly, piece by piece. I should say clearly what kind of journey this is, so you can settle into it properly. This is not a horror story, even though it visits the death of everything. The universe operates on rules far stranger than our fears, and the strangeness, once you let it in, is not frightening, but freeing. We are not here to be scared of the dark. We are here to walk into it slowly, with our eyes open, and to discover that the dark is doing something we never expected, something patient and recurring and almost gentle. So if part of you tightens at the thought of endings, let that part rest. Nothing we find tonight is an enemy. It is only the universe, being far larger and far stranger and far less final than the small word we use to contain it. Tonight we are going to walk all the way to the end of time, as far as physics can take us, and then we are going to keep walking past the point where the textbooks usually stop. We are going to watch the universe die in complete detail, so that you feel how total that death really is. And then we are going to watch the strangest thing of all, which is the universe quietly refusing to stay dead. We will move slowly, because there is no hurry. We have, quite literally, all the time there is. So let yourself settle in, and let me start by telling you how the universe is supposed to die, because you cannot feel the wonder of an ending that never comes until you have first stood at the ending everyone expects. Part 2. How the universe is supposed to die. Let me give you the standard story first, the one that comes from our very best measurements, because it is genuinely one of the most extraordinary things human beings have ever worked out. We did not guess at the fate of the universe. We measured our way toward it. The universe is expanding. We have known this since the late 1920s, when astronomers noticed that distant galaxies are rushing away from us, and the farther away they are, the faster they go. The whole thing is getting bigger, every galaxy drifting away from every other galaxy as the space between them stretches. For a long time, the open question was whether that expansion would slow down, stop, and reverse, or whether it would coast along forever. Gravity, after all, pulls inward. You might expect the collective gravity of everything in the universe to gradually put the brakes on the expansion, the way a ball thrown into the air slows as it rises. Then, in 1998, two teams of astronomers measured the expansion using distant, exploding stars, and they found something that genuinely shocked them. The expansion is not slowing down, it is speeding up. Something is pushing the universe apart faster and faster, overwhelming the inward pull of all the gravity in existence. We do not really know what that something is, so we gave it a placeholder name. We call it dark energy. And by our best current accounting, dark energy makes up roughly 68 to 69% of everything there is. The galaxies, the gas, the stars, all the ordinary matter, and all the mysterious dark matter combined are the minority. Most of the universe is this strange, repulsive energy of empty space, and it is winning. If dark energy is what it appears to be, an unchanging energy woven into the fabric of space itself, then the future is sealed, and it is a lonely one. The expansion will continue, faster and faster, and over billions of years the distant galaxies will be carried away from us so quickly that their light can no longer cross the growing gap. One by one, they will redden, dim, and vanish from the sky, not because they are gone, but because the space between us is stretching faster than their light can travel across it. A future astronomer, far enough ahead in time, would look out and see only an empty cosmos, with no evidence that there was ever anything beyond their own island of stars. The universe is, in a sense, slowly hiding itself from itself, and that is only the beginning of the dying. To see the rest, we have to leave behind the comfortable scale of billions of years and start counting in a way that breaks the human mind. From here on, the numbers are so large that we cannot write them out the normal way. We have to write them as powers of 10. A power of 10 is just a 1 followed by some number of zeros. 10 to the second power is 100, a 1 followed by 2 zeros. 10 to the ninth power is a billion. And the stages of the universe's death are written in powers of 10 stacked on powers of 10, where each stage lasts roughly 10 times longer than the one before it. Two physicists, Fred Adams and Gregory Laughlin, mapped this out in detail in 1997, and they divided the future into a series of long, fading ages. Let me walk you through them, because each one is a kind of funeral for a different part of reality. Hold one comparison in mind as we walk these ages, because it reframes everything. The age of stars, the one chapter of cosmic history with light in it, the only chapter in which life as we understand it could possibly exist, is by far the shortest of them all. If you imagine the full span from the first star to the final evaporation of the last black hole laid out as a single long line, the bright star-filled portion is a sliver at the very start, so thin you could miss it. Almost the entire line is darkness. We are not living in a typical moment of the universe's history. We are living in the rarest possible moment, the brief flash of warmth and light near the beginning, before the long, cold, dark majority of time that makes up nearly all of what there is. Whatever the universe mostly is, across its whole existence, it is not what we see around us now. It is the dark that comes after. We live right now in what they called the stelliferous era. It is the age of stars, the brief, bright chapter when the universe is full of light. It feels permanent to us, but it is not. It is a flash near the very beginning. The stars are burning through their fuel, and new stars are forming more and more slowly as the gas runs low. The most miserly, longest-lived stars are the small red dwarfs, which sip their fuel so slowly that they can shine for trillions of years. But even they run out. Roughly 100 trillion years from now, which is 10 to the 14th power years, the last red dwarf will flicker, fade, and go out. And when it does, for the first time in the entire history of the universe, there will be no starlight anywhere. The age of stars will be over, and it will never come again. After that comes the degenerate era, running from about 10 to the 14th power years to 10 to the 40th power years. The universe in this age belongs to the remnants, the corpses the stars leave behind. White dwarfs, the cooling embers of dead stars, slowly fade from white to red to black. Neutron stars sit in the dark, impossibly dense. Dead planets drift around dead suns. There is no new light being made, only the last residual glow of objects slowly giving up their heat to the cold. And during this era, if a certain prediction is correct, even matter itself begins to dissolve. Many theories suggest that the proton, one of the basic building blocks of every atom in your body, is not perfectly stable, that it will eventually decay into lighter particles. We have never actually seen a proton decay. Experiments have only been able to establish that if it happens, its half-life is at least 10 to the 34th or 10 to the 35th power years, which is so long that no proton has likely decayed in the entire history of the universe so far. But across the timescales we are now discussing, that slow dissolution would gradually take apart the dead stars and planets, atom by atom, until ordinary matter is mostly gone. Then comes the black hole era, from about 10 to the 40th power years to 10 to the 100th power years. By now, the ordinary matter has mostly evaporated away, and the only large structures left in the universe are black holes, the dark, silent remnants of the largest collapses. For a while, they reign. They are the last things standing. But they too are dying, just very, very slowly. Black holes are not perfectly black. The physicist, Stephen Hawking, showed that they slowly leak energy at their edges, radiating away their mass over time in what we now call Hawking radiation. The bigger the black hole, the slower it leaks. A black hole the mass of our Sun would take about 10 to the 67th power years to fully evaporate. A monster supermassive black hole, the kind that sits at the center of a large galaxy with 100 billion times the mass of the Sun, would take something like 2 times 10 to the 100th power years to finally disappear. But they do disappear. One by one, over these unfathomable spans, the black holes evaporate, each one ending in a final faint flicker as the last of it radiates away. Let me slow down on the black hole era for a moment, because it is the loneliest and most patient chapter in the whole history of everything, and it deserves to be felt rather than summarized. Imagine the universe at, say, 10 to the 80th power years from now. There are no stars. There have been no stars for an almost unthinkable span. The galaxies are gone, not just dark, but dispersed, their matter long since fallen into the great central black holes or flung out into the expanding emptiness. What remains is a scattering of black holes, separated by distances so enormous that each one is utterly alone, with no neighbor it could ever reach or even see. And each of those black holes is slowly, slowly fading, leaking a faint whisper of Hawking radiation into the dark, a glow so dim and so cold that calling it light would be generous. A black hole does not die in an instant. It spends almost its entire existence barely changing, leaking imperceptibly, and only at the very end, after 10 to the 67th or 10 to the 100th power years, does it finally shrink to nothing in a last faint flicker. Picture that final flicker, the last evaporation of the last black hole, the last event of any consequence anywhere in the universe. After it, nothing. That flicker is, in the standard story, the closest thing the cosmos ever has to a final act, and it happens in total darkness, with nothing to witness it, an ending so quiet that the word ending feels almost too loud for it. And then there is the last age, the dark era, everything beyond 10 to the 100th power years. There are no stars, there are no planets, there are no black holes. There is nothing but an incredibly thin, cold soup of stray particles and low-energy radiation drifting apart in the dark as the expansion carries everything ever farther from everything else. This is the heat death in its full and final form. Nothing burns, nothing falls, nothing collides, nothing changes. Every difference has been smoothed away. Every store of usable energy has been spent. The universe has become a smooth, cold, silent nothing. And according to the standard story, it stays that way, unchanging, for the rest of eternity. There is an even longer and stranger story hiding inside that picture, and it turns on a single unanswered question, the question of whether the proton truly decays. We do not know the answer. If the proton is perfectly stable, if it never breaks down, then the dead stars do not dissolve into radiation at all. Instead, something almost unbelievably slow takes over. Inside the cold, solid corpses of former stars, atomic nuclei can very rarely tunnel toward one another and fuse, a quantum process so glacial that it operates on a timescale of about 10 to the 1500th power years. That is a 1 followed by 1500 zeros. Across that span, the matter patiently reshuffles itself toward the single most stable element there is, iron. The dead stars become, over an eternity, cold spheres of iron drifting in the dark. Physicists actually call them iron stars, and they may be the last solid objects the universe ever makes. Only about 1% of all the stars that ever lived, frozen at last into the most settled arrangement matter can find. And there is one more number, larger than all the rest, that I have to give you, because it is the strangest entry in the entire catalogue of the universe's death. Given enough time, even a cold iron star is not stable. Its matter can quantum tunnel, particle by particle, into a black hole, collapsing under its own gravity through a process that ordinary physics would say takes essentially forever. The estimate for how long this takes is 10 to the power of 10 to the 76th power years. That is not a metaphor, and it is not loose talk. It is 10 raised to a power that is itself a 1, followed by 76 zeros. At those timescales, the very line between solid matter and a black hole begins to blur, because given enough eternity, everything becomes a black hole, and then every black hole evaporates, and then there is nothing. These numbers are not here to frighten you. They are here so that you feel, in your body, how much time the universe has after we are gone, and how complete the emptiness at the end of it really is. I want you to sit in that for a moment, because it matters that you feel how complete it is. This is not a small ending. This is the most total ending imaginable, the erasure of every star and every world and every black hole, the draining away of everything that ever made anything happen. If the standard story is right, this is the destination. This is where it all goes. And almost everything that has ever existed, or ever will, lies in that long, dark, empty future, not in the brief, bright flash where we happen to live. We are not the main event. We are the opening sentence, and the rest of the book is darkness. Part 3. 3 different words for one small word. Now that you have stood at the end, I want to go back and pick up that word I asked you to hold up to the light, end. Because here is where the certainty begins, very quietly, to crack. I want to be precise here, because precision is what cracks the certainty open. Sloppy thinking keeps the 3 meanings fused, and as long as they are fused, the ending looks total and obvious. But the moment you pull them apart and lay them side by side, you see that they do not stand or fall together, that you can grant 2 of them completely and still have the 3rd left entirely open. That is the move that turns a closed door into a question. So let us pull them apart, carefully, one at a time, and see which ones the physics actually forces on us, and which one we have only been assuming. When we say the universe ends in heat death, we are actually saying 3 different things at once, and we have never bothered to separate them. The first thing we might mean is the end of structure. That is the part you just watched. The last star, the last planet, the last black hole, all the interesting arrangements of matter, gone. No more things. That ending is real, and the timeline for it is the one we just walked. But the end of structure is not the end of the universe. It is the end of stuff happening in the universe. The stage goes dark, but the stage is still there. The second thing we might mean is the end of usable energy. This is a subtler idea, and it comes from thermodynamics, the branch of physics that deals with heat and energy and order. There is a quantity called entropy, which you can think of as a measure of how spread out and disordered and unusable the energy in a system has become. The universe is constantly moving from order toward disorder, from concentrated, usable energy toward spread out, useless energy. A hot cup of coffee in a cold room always cools down to room temperature, never the other way around. The heat death is the moment when the entire universe reaches that room temperature state, when everything is the same temperature everywhere, and there are no more differences to exploit, no more energy that can be used to make anything happen. Physicists call this maximum entropy. It is sometimes described as the moment when time loses its meaning, because if nothing ever changes, there is no way to tell one moment from the next. And the third thing we might mean, the one that hides underneath the other two, is the end of time itself, the final moment, the last tick of the last clock, after which there is no after. And here is the thing that should stop you. Nothing in the heat death story actually requires this. The end of structure is not the end of time. The end of usable energy is not the end of time. You can have a universe in which all the stars have died, all the black holes have evaporated, all the energy has spread out into uselessness, and yet time simply keeps going. The clock does not stop. There is just nothing for it to measure. The universe goes on existing, cold and dark and empty, but it goes on forever. This matters because so much of our dread of the end is really dread of one specific version of it, the version where time itself stops and there is simply no more. But we have just discovered that this version is not what the standard physics actually describes. The physics describes a universe that empties out and then keeps going empty, with the clock still running and nothing left to time. That is a strange and lonely picture, but it is not the absolute nothing we feared. The absolute nothing, the true closing of time, was never in the equations. It was a shadow we cast onto them. And once you notice that the shadow is yours and not the universe's, the whole question changes character, from a fact to be accepted into a mystery to be explored. Do you see what just happened? We assumed that when the stuff ends, everything ends. But the stuff ending and time ending are not the same event, and physics gives us no reason to believe they happen together. In fact, in the standard picture, they emphatically do not. The standard picture is not a universe that stops. It is a universe that empties out and then continues. Empty, with no final moment, no closing curtain, no last page. The heat death is not the end of the story. It is the story running out of events, while the pages keep turning blank forever. There is a phrase I want to give you now, and I want you to remember it, because we are going to come back to it later when it means something more than it does right now. An ending is just an event you cannot see past. Think about what that really means. When you imagine the end of the universe, you are imagining a kind of edge, a boundary beyond which there is nothing to imagine. But maybe that edge is not in the universe at all. Maybe it is in you. Maybe the end is simply the place where your ability to see forward stops, the horizon of your imagination, and the universe carries on past it, the way the road carries on past the hill you cannot see over. An ending is just an event you cannot see past. There is a way to make this concrete, and it has to do with how we measure time at all. Time, in physics, is not some independent thing ticking in the background. We measure time by change. A clock is just something that changes in a regular way. A pendulum that swings, a crystal that vibrates, a particle that decays. Without change, there is no way to tell one moment from the next, and arguably no meaningful sense in which time is passing at all. Now, think about what that means for the heat death. At maximum entropy, when everything is the same temperature everywhere and nothing is left to change, every clock has stopped, not because time has ended, but because there is nothing left for time to measure. The universe enters a condition where moments are indistinguishable, where there is no before and no after, where time, in any sense we could detect, has gone strangely quiet without actually stopping. And yet the standard story says the universe persists in exactly that condition indefinitely. So, is that an ending or not? It has no events. It has no change. But it also has no final moment, no closing of the book. It is a kind of frozen forever, a permanent present with nothing happening in it. And whether you want to call that an end or call it an eternity may say more about you than about the physics. This is the first crack. It is small, but it is real. The certainty you walked in with, the certainty that the universe ends, has quietly split into pieces. The structures end? Yes. The usable energy runs out? Yes. But time ending, the universe truly stopping, the genuine no more, ever, that part was never actually in the physics. We smuggled it in ourselves, because it matched what we know about candles and summers and the people we love. And now that we have noticed we smuggled it in, we can take it back out and ask the real question, the one underneath. If time does not stop at the heat death, then what happens next? What does a dead universe do with an eternity of being dead? Part 4. The death that never arrives. Let me push on that crack, because it gets stranger the more weight you put on it. We have been talking about the heat death as if it is a place the universe arrives at, a destination, a final state it reaches and then sits in. But there is a real question about whether the universe ever actually arrives at the heat death at all. Think about how the dying actually works. The universe is expanding, faster and faster, and as it expands, everything spreads out and cools down. The temperature of the universe falls toward absolute zero, the coldest possible temperature. But here is the thing about approaching absolute zero. You never quite get there. It is like one of those mathematical curves that draws closer and closer to a line without ever touching it. The universe gets colder and colder and colder, halving and halving its temperature over enormous spans of time, but the halving never finishes. There is always a little further to fall. The cold keeps falling forever and never completes. Mathematicians have a word for a line that something approaches forever without ever reaching. They call it an asymptote. And there is a real and serious sense in which the heat death is not an event, but an asymptote, a state the universe forever approaches and never actually attains. The last black hole takes 10 to the 100th power years to evaporate, but even after that, the universe keeps spreading, keeps cooling, keeps fading, and there is no moment you can point to and say, there, that is the instant it finished. There is no finish. There is only an endless approach. I want you to feel how disorienting that is, because it overturns the most basic picture we have of an ending. We picture an ending as a final moment, the last breath, the last note of the song, the last page, and then the cover closes. We assume that if something ends, there is a specific instant that is the end, after which there is no more. But the universe may not work that way at all. The universe may have no final moment. It may have, instead, a moment that is forever almost the last, and then another moment that is even more almost the last, and another, each one closer to the end than the one before, the whole sequence reaching toward an ending that never actually comes. This is one of those ideas that sounds like a word game until you sit with it, and then it becomes vertiginous. You have spent your whole life afraid of, or at peace with, or simply resigned to, the idea that things end. The end is the thing you brace for. But what if the end is not a wall you eventually hit? What if it is a horizon, the kind that retreats as you walk toward it, so that you can walk for all of eternity and never once arrive? The thing you were bracing for is not there. There is no wall. There is only the walking, and the walking has no last step. This is also where a familiar word from earlier nights returns with new force, the word asymptote, because it changes the geometry of the ending in a way worth holding clearly. An ordinary ending is a point. You can mark it on a timeline. But an asymptotic ending is not a point at all. It is a direction, a leaning, a tendency the universe expresses forever without ever completing. If you tried to draw it, you would not draw a line that stops. You would draw a line that bends closer and closer to the floor and runs on past the edge of the page, never touching, never finishing. And the universe, in this picture, is that line. It is always getting closer to its death, and never arriving, so that at every single moment in the infinite future, the death is still ahead, still approaching, still not yet here. The end is permanently in the future, which is a very strange way of saying that, in a sense, it never actually happens at all. And notice what this does to the fear. So much of our dread about endings is really dread about a specific final moment, the instant of no more. But if there is no final moment, if there is only an endless approach, then the moment you were dreading does not exist. It was never going to come. The universe does not slam shut. It thins and fades and cools and goes quiet and keeps doing so gently without ever reaching the bottom, because there is no bottom to reach. You can even put numbers on the endlessness of the approach. The temperature of the universe falls in a way that is roughly exponential, halving over a certain span, then halving again over a longer span, then again, each halving taking longer than the last. After 1 trillion years, the universe is far colder than today. After a number of years written as a 1 with 100 zeros, colder still. After the tower of exponents we will reach later tonight, colder again, and yet never, at any finite moment, exactly at absolute zero. The remarkable thing about this kind of curve is that it contains an infinity inside a process that never finishes. There are infinitely many halvings still to come, no matter how far out you go. Pick any moment in the future, however distant, and there is always a colder, emptier, later moment beyond it, and beyond that one another, with no last term in the series. The universe does not run out of future. It runs out of things to do with its future, which is not the same thing at all. Now, I am not telling you this to comfort you, exactly, because there is something lonely in it too. An endless fading is still a kind of dying, even if it never completes. But I am telling you this because it is the first place where the simple story, the story where the universe ends, stops being simple. The honest physics does not give you a clean, final ending. It gives you something far stranger, a death that is always approaching and never arrives, a last page that keeps not being the last. And once you accept that the universe might never actually finish dying, you have to ask the next question, the one that turns the whole picture inside out. If the universe lasts forever, even as a cold and empty thing, then forever is a very, very long time for nothing to happen in. And it turns out that over a long enough forever, nothing has a way of not staying nothing. Part 5. The Twitch in the Dark. So let us go there. Let us go all the way out, past the last star, past the last black hole, into the dark era, and let us stay there, because almost everything that will ever exist exists in this age, and we have barely looked at it. The universe in the dark era is the emptiest thing you can imagine, and then emptier than that. Picture a volume of space larger than everything we can currently see, and in that entire enormous region, a single particle, then nothing for a span you cannot picture. Then maybe another particle, drifting, never meeting the first, because the expansion is carrying them apart faster than they could ever drift together. There is no heat to speak of, no light worth the name, no events. The cold is almost, but not quite, absolute, and this state does not last for a while. It lasts, in the standard story, forever, an eternity of perfect, uninterrupted nothing. But here is where a strange and beautiful theorem comes in, an old result from the 1890s worked out by the French mathematician Henri Poincaré. Poincaré was studying systems that are closed, meaning nothing enters or leaves them, and finite, meaning they have only so many possible arrangements, and he proved something remarkable. He proved that any such system, if you wait long enough, must eventually return to a state arbitrarily close to where it started. Not might, must. Given enough time, a closed, finite system cycles back, again and again, through configurations close to every configuration it has ever had. This is called the Poincaré recurrence theorem, and it has a haunting consequence for a universe that lasts forever. If the observable universe is, in the relevant sense, finite and closed, then the heat death is not actually the end of the story, even as an empty state. Because over a long enough span, the random jostling of the particles and the random flickering of the quantum fields will, purely by chance, stumble back into an arrangement of lower entropy, an arrangement with order in it, an arrangement that has not existed since the universe was young. The dead universe twitches. Out of the perfect, smooth, maximum entropy dark, a fluctuation appears. Particles that have drifted meaninglessly for an eternity happen, by sheer chance, to fall into a pattern. For no reason at all, order returns to a universe that had finished with order forever ago. Imagine it with me, because it is one of the strangest things in all of physics. You are in the dark era. There is nothing. There has been nothing for a span of time so long that the numbers describing it stop meaning anything, and we will get to those numbers in a moment. The cold is total. The silence is total. Every direction looks exactly like every other direction, the same, featureless, thin, nothing, forever, and then a stirring. A few particles, by pure accident, drift into a configuration they have not held since before the stars died. A faint patch of order, glimmering for an instant in a universe that had forgotten what order was. It does not last. It dissolves back into the dark. But it happened. The corpse moved. And if it can happen once, then over an eternity it happens again, and again, and again, an endless series of tiny resurrections in the long dark, none of them lasting, all of them impossible, all of them certain. Before the numbers, I want you to feel the patience this requires, because patience is the wrong word, and there is no right one. We are not talking about waiting a long time. We are talking about waiting so long that the entire history of the universe, up to now, all 13.8 billion years of it, from the Big Bang through the formation of stars and worlds and us, would not even register as the first faint instant of the wait. We are talking about a span next to which the lifetime of a star, the lifetime of a galaxy, the lifetime of a black hole are all rounding errors, all effectively zero. And yet, on the scale of forever, even that span is nothing, because forever is not a long time. It is not any amount of time at all. It is the absence of an end to time. And it is against that absence, that genuine forever, that the recurrence becomes not just possible, but certain. Now let me give you those numbers, because they are part of the wonder. How long do you have to wait for a significant Poincaré recurrence in a universe like ours? A physicist named Don Page tried to estimate it, and the answer he got is one of the largest numbers ever to appear in a serious scientific paper. It is not 1 billion years. It is not 10 to the 100th power years. It is 10 to the power of 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 2.08. Let me try to convey what that means, even though it cannot really be conveyed. It is a tower of exponents, a power of a power of a power of a power. The number of zeros in that number has more zeros in it than you could write if you used every particle in the observable universe as a digit. It is a number so large that there is no physical thing it could ever count. And yet, crucially, it is not infinite. It is a specific, finite length of time, which means that if the universe truly lasts forever, then that span of time will pass, and pass again, and pass an unlimited number of times. The recurrences are not maybes. On an infinite timeline, they are guaranteed, over and over, without end. There is a quiet lesson buried in these impossible numbers, and it is one the universe keeps teaching at every scale. Our intuition is built for the human-sized world, for spans of seconds and years, and at most a lifetime, and it simply has no grip on quantities like this. When we hear 10 to the 100th power years, our minds round it to forever, and when we hear the recurrence time, our minds round that to forever too, and so we lose the most important distinction of all, the distinction between very large and truly infinite. They feel the same to us, but they could not be more different. A very large number, however monstrous, eventually passes. Infinity does not pass, because it is not a duration. And almost everything strange about the fate of the universe lives precisely in that gap our intuition cannot feel, the gap between numbers too big to picture and a forever that is not a number at all. This is the moment when the powers of 10, stacked on powers of 10, stop being just very long and start being something else entirely. Back at the heat death, the numbers were enormous, but you could still, in principle, write them down. 10 to the 100th power is a 1 with 100 zeros. You could write it on a chalkboard. But this recurrence number, this tower of exponents, cannot be written down at all, not on any chalkboard, not in any book, not using all the matter there is. The number itself is too big to exist physically. And that is the first hint of something we will see again, more profoundly later tonight. At the far edges of time, the numbers we use to measure things grow so large that measurement itself starts to break down. The scale of the universe outruns our ability to hold it. And there is a wilder version of this still. Some physicists have asked what the most interesting thing is that a random fluctuation could produce. A patch of order is one thing. But, over a long enough eternity, a fluctuation could, in principle, produce something far more dramatic, a tiny region of space that happens to fall into exactly the right configuration to begin inflating, to begin expanding rapidly, the way our own universe did in its first instant. In other words, a fluctuation in the dead universe could give birth to a brand new Big Bang. The cosmologist Sean Carroll and others have explored exactly this kind of scenario, in which a cold and empty cosmos is not a graveyard, but a womb, endlessly, randomly, giving rise to new baby universes out of its own emptiness. The dead universe does not just twitch. Sometimes the twitch becomes a birth. It is worth slowing down on just how strange the recurrence really is, because it sits at the boundary between the certain and the unimaginable. The mathematics is not in doubt. Poincaré's theorem is a proven result, as solid as anything in physics, and it says without hedging that a finite, closed system must return near its starting state. What staggers the mind is the scale on which it operates. There are actually two enormous timescales hiding here, and physicists distinguish them. The first is the time you would wait for a modest fluctuation, a small patch of order flickering out of the dark. The second is the full Poincaré recurrence time, the time you would wait for the universe to return close to an entire earlier configuration of itself, and that is the tower of exponents we just met. Both are finite. Both are guaranteed on an infinite timeline, which means that if the universe truly lasts forever, then not only do small fluctuations happen, but the universe returns, again and again, near states it held long ago, an unlimited number of times, with unlimited variations forever. And there is a quiet philosophical knife hidden in that, which is worth naming. If every possible configuration recurs, given enough time, then somewhere in that endless future, there are fluctuations that reproduce this exact moment. This room, this voice, you lying there, hearing these words, not metaphorically, but as a literal, statistical consequence of an eternal, finite, fluctuating universe. It would not be you in any continuous sense, just an arrangement of particles identical to the arrangement that is you right now, assembled by chance out of the dark, complete with the memory of having always existed. Physicists do not find this comforting. They find it alarming, because a universe that produces such things too easily starts to undermine our confidence in everything, and we are going to see exactly why in a little while. So already, before we have touched a single one of the grand cyclic theories, the simplest physics of a universe that lasts forever has handed us something astonishing. Even if the universe truly dies, even if every star and every black hole is gone, and only the cold dark remains, the cold dark does not stay still. It cannot. Given forever, nothing has a way of not staying nothing. And if even the emptiness refuses to be final, then maybe the ending we have been imagining was never an ending at all. Maybe it was just the longest, quietest part of a story that does not know how to stop. Part 6. Maybe it happens again. The Poincaré recurrence is what you get for free, with no new physics, just time and patience. But there are physicists who think the universe does something far more orderly than a random twitch in the dark. They think the universe does not merely flicker back to life by accident. They think it begins again, deliberately, completely, as a matter of how the cosmos is built. They think the universe is cyclic, that it has happened before, that it will happen again, and that the Big Bang we point to as the beginning was not a beginning at all, but a transition, a handoff from a universe that came before. There is a reason this idea keeps returning to the human imagination across every age and culture, and it is worth naming before we get technical, because it tells you something about us. A universe that only ends feels, to most people, unbearable in a way that a universe that turns does not. The wheel, the cycle, the return, the breathing in and out, these images comfort us because they fold the ending back into a larger pattern that does not end. The line that simply stops feels like loss. The circle that comes around feels like meaning. We should be a little suspicious of how much we want the cyclic answer to be true, because wanting a thing does not make it real. But we should also notice that some of the most careful physicists alive have found, in the cold language of mathematics, reasons to take the oldest comfort seriously, and that is a remarkable convergence between what we long for and what the equations permit. This is an old dream, and you can find versions of it in ancient cosmologies all over the world. The idea of a universe that breathes in and out, that dies and is reborn in an endless wheel. But what makes the modern versions worth taking seriously is that they are not poetry, they are mathematics. They are attempts to write down, in the language of physics, how a universe could end and begin again without ever passing through a true final stop. Let me show you two of them. The first comes from two physicists, Paul Steinhardt and Neil Turok, who proposed it in the early 2000s. Their model grows out of string theory, the idea that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and out of a larger framework called M-theory, which suggests that our familiar three-dimensional universe might be a kind of membrane, a sheet, floating in a space with more dimensions than we can see. They call such a membrane a brain, dropping the first part of the word, and in their picture there is not just one brain. There are two parallel universes separated by a tiny gap across a hidden dimension, like two enormous sheets hanging next to each other in a space we cannot perceive. Take a moment to appreciate how different this is from the explosion most people picture when they hear the words Big Bang. The Big Bang was never an explosion in space, never a bomb going off at a point with empty space around it waiting to be filled. It was an event that happened everywhere at once, the sudden, hot, dense beginning of all of space, filling all of space, with no outside and no center. The brain collision captures this perfectly, because two membranes meeting do not meet at a point, they meet everywhere along their whole extent simultaneously. The entire universe ignites in the same instant, at every location, which is exactly what the real Big Bang appears to have done. Whatever else you think of the model, it gets that crucial feature right, and that is part of why serious physicists were willing to take it seriously in the first place. In the Steinhardt and Turok model, these two brains are not still. They drift slowly toward each other across the hidden dimension, and eventually they collide. That collision, spread across the entire expanse of the brain, releases an enormous amount of energy everywhere at once. And that, in their picture, is what we experience as the Big Bang. Not a single point exploding, but a collision filling all of space simultaneously. After the collision, the brains drift apart again. Our universe goes through its long life of expansion and cooling and the formation of stars and galaxies. And then, across unimaginable spans, the brains slowly approach once more and collide again, and the cycle repeats. Each cycle includes a long phase of slow, accelerated expansion, the same kind of expansion our dark energy is producing right now, and that phase serves a purpose. It smooths the universe out, flattens it, dilutes away the debris of the previous cycle, and sets up clean initial conditions for the next collision. The mathematics make the cycle stable, an attractor, a pattern the universe naturally falls back into rather than away from. And so it can repeat, not once or twice, but indefinitely, with no first collision and no last one. A universe with no beginning and no end, only an endless rhythm of approach, collision, expansion, and approach again. What I find moving about the brain model, beyond its mathematics, is the image at the center of it. Two universes, hanging side by side across a dimension neither can perceive, drifting toward each other over spans of time that dwarf everything, and meeting, finally, in a collision that neither universe experiences as a collision but as a birth, as a Big Bang, as the first bright morning of a new world. From inside, you would never know you had been struck by another universe. You would only know that everything began. The violence of the model, from the outside, is the gentleness of a beginning from the inside. And there is something almost tender in that. Two lonely sheets of reality reaching across the dark and, in touching, making everything that will ever exist. The second model takes a completely different route to a similar place, and it comes from a field called loop quantum cosmology. To understand it, you have to understand what is wrong with the Big Bang in the standard picture. When physicists run the expansion of the universe backward, rewinding the clock toward the beginning, everything gets denser and hotter and more compressed, until, right at the first instant, the equations say the density becomes infinite. Everything in an infinitely small point of infinite density. This is called a singularity, and a singularity is not really a thing. It is a sign that the theory has broken. When your equations start spitting out infinities, it means you have pushed them past the point where they work. General relativity, our theory of gravity and space and time, simply stops making sense at the Big Bang singularity. It throws up its hands. Loop quantum cosmology tries to fix this by bringing in the rules of quantum mechanics, the physics of the very small, and applying them to the universe as a whole. And when physicists like Abhay Ashtekar and Martin Bojuel did this, they found something wonderful. The singularity goes away. Instead of the density climbing to infinity, it climbs to a finite maximum and then rebounds. Run the clock backward, and the universe does not hit an infinitely dense wall. It reaches a state of incredible but finite density, and then it bounces, which means there was a before. The Big Bang was not the beginning. It was a bounce, a rebound, from a previous universe that had been contracting, collapsing inward, until it reached the maximum density and sprang back outward into the expansion we call our Big Bang. They call it the Big Bounce. And in this picture, our universe is just the latest in a possibly endless sequence, each one collapsing and bouncing into the next. Imagine standing inside that contraction in the universe before ours in its final age. For most of its history, it looked like ours, full of galaxies drifting apart. But then the expansion reversed, and everything began to fall back together. The galaxies stream inward. The sky, which had been dark and cold, begins to brighten and warm as everything compresses. The temperature climbs. The density climbs. You are racing toward what general relativity insists must be a wall, a singularity, the end of everything. And then, Instead of a wall, you find a floor. The universe reaches its maximum density, holds for the briefest instant, and rebounds. And what felt like the end becomes, on the far side, a beginning. The crunch you were bracing for turns out to be a bounce. But there is a catch in the bounce, and it is a poignant one. Bojewald found that the bounce does not preserve everything. Some of the information about the universe before the bounce gets scrambled, lost, rendered unrecoverable on this side. He gave it a beautiful and melancholy name. He called it cosmic forgetfulness. The universe might remember that there was a before, in the sense that the bounce implies one, but it cannot fully reconstruct what that before was like. The bridge across the bounce is real, but it is shrouded in fog. The previous universe is gone in every way that matters, even though it gave birth to this one. Hold on to that idea, cosmic forgetfulness, because when we ask later what it would really mean for the universe to repeat, that fog is going to turn out to be the most important thing in the room. The two models solve a problem that any cyclic theory has to confront, and it is worth understanding because it is the reason naive cyclic universes do not work. The problem is entropy. We said earlier that the universe always moves from order toward disorder. That entropy always increases. If that is true, then a simple cycling universe runs into trouble immediately, because each cycle should inherit all the accumulated disorder of the cycle before it, piling up more and more entropy until the cycles get longer and more degenerate, and the whole thing grinds toward heat death anyway. A merry-go-round that never resets cannot turn forever. So the serious cyclic models all have to do something clever about entropy, some way of resetting the books between cycles, and how they do it is what separates them. In the Steinhardt and Turok model, the trick is in the expansion. Each cycle includes that long phase of slow, accelerated expansion, driven by something very much like the dark energy we observe right now, and that expansion dilutes the disorder of the previous cycle almost to nothing, spreading it so thin across the enormous stretch space that when the brains collide again, they collide in a clean, smooth, low-entropy state, ready to begin fresh. The entropy is not destroyed, it is diluted away into the vastness, swept under an ever larger rug. In the bounce models, the reset happens differently, in the extreme conditions at the bounce itself, where the ordinary rules are suspended and the universe is wiped toward a smooth beginning. Both are attempts to answer the same ancient objection, the objection that a wheel must wear down, and both answer it by finding a way for the universe to clean its own slate. There is something almost satisfying about that, after the long bleakness of the heat death. The standard story gave us a universe that runs down once, like a clock that is wound a single time and then ticks towards stillness. The cyclic models give us a universe that rewinds itself, that has found a way to keep going, that turns the running down into part of a larger turning. And whether or not either model is correct, and we genuinely do not know, they prove something important just by existing. They prove that a universe with no beginning and no end is not a contradiction, not a fairy tale, but a thing you can write down in real equations that real physicists take to real conferences. The endless universe is, at the very least, allowed. So now we have two serious mathematical models in which the universe does not end but begins again. The brains collide, over and over. The universe bounces, over and over. Different mechanisms, different mathematics, but the same astonishing claim that the Big Bang was not the start, and the heat death, if it even comes, is not the finish, and the whole thing is a cycle that has been turning, perhaps, forever. And yet, as strange as these already are, neither one is the strangest. The strangest idea of all does not say the universe collides or bounces. It says something far more subtle and far more dizzying. It says that the end of the universe and the beginning of the universe are, when you look closely enough, literally the same thing. Part 7. When the End Becomes the Beginning. I have saved this one for the middle of our journey because it is the strangest and the most beautiful idea in the whole subject, and I want you to be ready for it. It comes from Roger Penrose, one of the most important physicists of the last century, a man who won the Nobel Prize in 2020 for his work on black holes, who spent his career proving rigorous, careful theorems, not chasing wild speculation, and late in his life, Penrose proposed a model so audacious that when you first understand it, it feels like a trick. He calls it conformal cyclic cosmology, and its central claim is this: the heat death of our universe will become, without anything in between, the Big Bang of the next. It helps to know who is making this claim because it changes how you weigh it. Roger Penrose is not a fringe figure. He worked alongside Stephen Hawking on the theorems that established black holes must contain singularities. He invented mathematical tools that physicists still use every day, and he won a share of the 2020 Nobel Prize in Physics for that black hole work. When a man with that record, late in a long and careful career, sits down and writes a book called Cycles of Time, arguing that the end of the universe is the beginning of the next one, you cannot simply wave it away as a daydream. You have to take it seriously, examine it, and decide whether the argument holds, even if your instinct screams that it cannot be right. That is exactly what the physics community has done, with a mixture of admiration and doubt, and it is what I am going to ask you to do now. To feel why this is not a trick, you have to go back out to the very far future, to the heat death, and look at it with fresh eyes. Picture the universe at the end, after every black hole has evaporated, after every massive particle has decayed or been diluted into oblivion. What is left? Almost nothing. But that almost nothing is mostly made of one kind of thing: light. Photons, the particles of light, and gravitons, the particles of gravity, drifting through an endless, cold, expanding space. And photons and gravitons have a special property. They have no mass. They are massless. And massless particles, it turns out, live in a very strange world. Here is the strangeness. A massless particle, like a photon, does not experience the passage of time. From the photon's own point of view, it is emitted and absorbed in the same instant, no matter how far it travelled or how long we, watching from outside, measured the trip to take. Time, for a photon, does not pass. And there is something even more important for our purposes. A universe made only of massless particles has no way to measure size. Think about what it takes to measure size. You need a ruler, something of a definite length to compare against. You need a clock, something that ticks at a definite rate. But mass is what gives particles a definite scale, a definite size, a definite rate of ticking. In a universe with no mass at all, there are no rulers and there are no clocks. There is nothing to measure size against. And Penrose's startling insight is that in such a universe, the very idea of size stops being meaningful. The difference between enormous and tiny, between a span of empty light years and the width of an atom, requires something to compare against. And in a universe of pure, massless radiation, there is nothing to compare against. Big and small lose their meaning. I want you to sit inside that for a moment, because it is the conceptual center of the whole idea. Imagine you are the last photon, crossing an infinite, cold, dilute universe at the end of time. There is nothing else. No matter, no rulers, no clocks, nothing massive anywhere to give you a sense of scale. Now try to answer a simple question. How big is the universe around you? You cannot answer. There is nothing to measure it against. Try to answer how much time has passed. You cannot answer. You do not experience time, and there is nothing ticking to count it. In your world, the world of the last light, the words big and small, long and short, have quietly stopped meaning anything at all. And in that moment, something extraordinary becomes possible. Because if size has no meaning, then the cold, infinitely spread out, infinitely dilute end state of the universe, where everything is so far apart it might as well be nothing, becomes mathematically indistinguishable from a hot, infinitely compressed, infinitely dense beginning state, a Big Bang. The two are connected by a mathematical operation called a conformal rescaling, which is a way of stretching or shrinking scales while keeping the underlying shape intact. Penrose argues that when you reach the end of an eon, the end of a complete cycle of the universe, the massless far future can be rescaled, smoothly and without passing through any true singularity, into the dense, hot beginning of a brand new eon, a new Big Bang. The end does not lead to the beginning. The end is the beginning. They are the same mathematical state, seen at two different scales, and at the very end, scale is the one thing that no longer exists to tell them apart. Let that land, because it is the answer to the question we started with, taken to its absolute limit. There is no end. Not because the universe avoids the heat death, but because the heat death itself, the coldest, emptiest, most final state imaginable, turns out to be identical to the most fertile, most explosive, most beginning state imaginable, the most desolate thing in all of physics, and the most creative thing in all of physics are written with the same equation. The darkest dark and the first dawn are the same place, approached from two directions. The universe ends, and in ending, without any gap, without any pause, without anything happening in between, it begins. I want to be honest that conformal cyclic cosmology is a minority view, and that many cosmologists regard it with skepticism, not because it is foolish, but because the leap it asks for is so large and the evidence so thin. To accept it, you have to believe that rest mass itself somehow fades away in the far future, that even the most stable particles eventually lose their mass so that the universe can become purely conformal, and we have no established physics that guarantees this. Penrose has proposed mechanisms, but they are speculative, and critics point to exactly this gap. I tell you this not to deflate the idea, but because the idea is more interesting when you see it honestly as a brilliant, contested, possibly wrong, possibly visionary proposal from one of the great minds of physics, rather than as a settled fact. Its beauty is not that it is proven. Its beauty is that it is even thinkable, that a careful person could look at the coldest end of everything and see in it, written in the same equation, the hottest beginning. And this is not just one cycle. In Penrose's picture, it is endless. Aeon after aeon after aeon, each one a complete universe that forms, grows old, fills with black holes, watches them evaporate, fades to massless light, forgets its own scale, and becomes the Big Bang of the next. There is no first aeon and no last one. The chain runs forever in both directions. Our Big Bang, the one we call the beginning of everything, was the heat death of a previous universe, an aeon that lived and died before ours and handed itself to us as our first instant. And our own heat death, the cold, empty future we walked to earlier tonight, is not our ending. It is the first morning of a universe that does not exist yet, that will never know we were here. I want to dwell on the role of black holes in this, because it is the part that makes conformal cyclic cosmology feel less like a trick and more like a genuine mechanism. Penrose has long been preoccupied with a puzzle about entropy and the beginning of the universe, the question of why our Big Bang was so extraordinarily smooth and ordered when, statistically, it had no business being so. His answer involves black holes doing something subtle to the universe's entropy across an aeon. As matter clumps together over cosmic history, it forms black holes, and black holes carry almost unthinkable amounts of entropy. Then, across the long black hole era, They evaporate through Hawking radiation, and in Penrose's accounting, this evaporation effectively removes that entropy from the reckoning, helping to deliver the smooth, low-entropy state needed for the next aeon to begin clean. The black holes are not incidental to the cycle. They are part of the machinery that resets it. The very objects that seem like the universe's final tombstones turn out to be the instruments of its renewal. And then there is the matter of the massless future, which is the part that asks the most of us. We have to accept that in the far future, with every massive particle gone, the universe genuinely loses its ability to measure scale, and that this is not a limitation of our instruments, but a real feature of a universe made only of light. Penrose's claim is that under those conditions, a mathematical symmetry called conformal invariance takes over, a symmetry that does not care about overall size, only about shapes and angles. In a world governed by that symmetry, stretching everything by an enormous factor changes nothing physical, and so the infinitely stretched cold end and the infinitely compressed hot beginning are not two states connected by a process. They are the same state, described twice. It is one of the boldest claims in modern cosmology, made by a man who spent his life being careful, and even his critics admit that it is not obviously wrong, only very hard to test. We will come to the testing and to the one dramatic attempt that was made before the night is out. There is a strange comfort and a strange loneliness braided together in that, and we are going to have to face both before the night is over. The comfort is obvious. There is no end. The story does not stop. The universe goes on forever in both directions, an unbroken chain of births and deaths that are the same event seen twice. But the loneliness is hidden in the details, and it is this. When our universe becomes the Big Bang of the next aeon, almost nothing of us crosses over. The conformal rescaling washes away nearly all the information, nearly all the structure, nearly everything that made our universe the particular universe it was. The next aeon does not remember us. It cannot. And that, the question of what survives the crossing, is where we have to go next. Part 8. One bubble in an endless sea. Before we face what is lost between the cycles, I want to widen the view one more time, because there is yet another way the universe might have no end, and it does not require the universe to repeat at all. It requires only that, somewhere, the beginning never stopped. To get there, we have to go back to the very first instant of our own universe, to a moment called inflation. In the leading account of the Big Bang, the universe began with an extraordinary burst of expansion, a fraction of a second, in which space itself ballooned outward at a staggering rate, doubling and doubling and doubling in size, faster than you can sensibly describe. This burst, called cosmic inflation, smoothed the universe out and stretched it flat and seeded it with the tiny ripples that would later grow into galaxies. Then, in our region, inflation ended, and the universe settled into the steadier expansion that has continued ever since. That is the standard story of our beginning. But many physicists who study inflation have come to a remarkable conclusion. Inflation, once it starts, may be almost impossible to fully stop. It ends in some regions, like ours, where it settled down and allowed galaxies and stars and us to form. But in the spaces between, inflation keeps going, expanding so furiously that it constantly creates more room for itself, more inflating space, faster than it can ever switch off everywhere. This is called eternal inflation. And in this picture, our entire universe, everything we have been discussing all night, every star and galaxy and black hole, the whole thing we walked from birth to heat death, is just one region where inflation happened to stop. One bubble, one pocket of calm in an endlessly inflating sea. And that sea is dotted with other bubbles, other universes, each one a place where inflation locally ended and a cosmos formed, and new bubbles are forming all the time, and they will keep forming forever. There is a way of feeling eternal inflation that makes it less like an abstract theory and more like a change of vantage. For most of this night, we have been standing inside our universe, looking forward toward its death and asking whether the death is final. Eternal inflation asks us to step outside, to imagine looking at our entire universe from beyond it, and to see it as one event among unlimited others, one bubble rising in a sea that has been bubbling forever. From that vantage, the question is everything ends becomes almost a category error, like asking whether the ocean ends because one wave breaks. The wave ends, the water does not. Our universe may break like a wave on some far shore of time, and the inflating ocean that raised it will go on raising others, indifferent, inexhaustible, having never noticed that one of its countless waves had risen and fallen, and that, briefly, something inside it had looked around and wondered whether it would last. Notice what this does to the question of an ending. Our bubble might end. Our bubble might freeze into heat death, or collapse, or do whatever our particular physics dictates. But the inflating sea that birthed us never ends. It cannot. It is, by its nature, eternal, always making more of itself, always sprouting new universes, with no final bubble and no last one. So even in the bleakest reading of our own fate, where our universe genuinely dies and does not come back, the larger structure we are embedded in goes on without us, endlessly fertile, endlessly beginning, an eternal foam of universes in which ours is a single bubble that rose, shimmered, and will eventually pop, while the foam itself never stops. This is a humbling place to stand, and I want to let you stand in it for a moment, because it keeps demoting us, gently, in a way that is somehow more freeing than frightening. We began the night thinking the universe was everything, and that its end was the end of everything. Then we found that our universe might be one aeon in an endless chain of aeons. And now we find that it might also be one bubble in an endless sea of bubbles. The thing we called the universe keeps turning out to be a small part of something larger that does not share its mortality. Whatever happens to us, to our stars and our galaxies, and our particular run of cosmic history, the larger process that made us appears to have no off switch. It was beginning before we began, and it will be beginning long after we have ended, if we end at all. This is the picture cosmologists sometimes call the multiverse, though that word has been worn smooth by overuse, so let me be careful about what it means here. It does not necessarily mean other dimensions or parallel worlds you could step into. It means, in this specific case, that the inflating sea keeps producing pocket universes, regions where inflation locally stopped, each forming its own enormous cosmos, and that this production never ceases. New pockets are forming right now, faster than the old ones can age, somewhere out in the inflating background that we can never observe because the space between us and it is, expanding faster than light, can cross it. Our pocket, our entire universe, is sealed off inside its own bubble, which is why the larger sea is invisible to us, and why this whole grand structure lives, like so much of tonight's subject, precisely in the places we cannot look. There is a famous difficulty with this picture, honest people should admit, called the measure problem. If there are endlessly many bubbles, infinitely many, then asking what is typical, what most universes are like, what most observers see, becomes mathematically slippery because comparing infinities is treacherous, and depending on how you do the counting, you can get almost any answer you like. Physicists have not fully solved this, and some regard it as a sign that eternal inflation, for all its appeal, is not yet a finished theory. I mention it not to undermine the idea, but to keep us honest. The endless sea is a serious proposal, but it comes with serious unanswered questions, and pretending otherwise would betray the very spirit of careful wonder this is supposed to be. And yet, widening the view does not actually answer the question that has been quietly building underneath everything. In eternal inflation, the sea goes on, but our bubble may still die, and the new bubbles are not us. They are strangers, brand new universes, with their own histories that have nothing to do with ours. In conformal cyclic cosmology, the eons go on, but almost nothing crosses between them. In the bounce, there is cosmic forgetfulness, the fog across the bridge. Again and again, no end turns out to come with a price, and the price is always the same. The universe may go on forever, but it does not carry anything with it. And so we arrive at the hardest and most human part of this whole story, the part that is not about black holes or brains or photons, but about what it actually means to continue when nothing is remembered. We have to ask what, if anything, is really saved when the universe has no end. Part 9. What nothing carries across. We have spent the night gathering reasons to believe the universe might not end, and they are real reasons, serious ones. But I have been holding back the hardest question, the one that turns the comfort of no end into something far more complicated, and it is time to face it directly. If the universe goes on forever, in cycles or in bubbles or in an endless approach to a death it never reaches, then what exactly goes on? What survives? What is carried across? The answer, in almost every one of these models, is astonishingly little. Let me show you why. Because it matters, and because it is the part that makes this more than an abstract puzzle. The pattern I am about to show you repeats across every model, so watch for it. In each one, the universe buys its continuation with forgetting. The price of going on is letting go of what came before, so completely that the going on cannot even be called a memory. This is not a flaw the theorists overlooked. It is, in most cases, the very mechanism that makes the continuation possible at all. The slate has to be wiped for the next universe to be written, and a slate that is truly wiped keeps nothing of what it held. So, as we walk through these, notice that the comfort of no end and the loss of everything are not opposites. They are the same fact, seen from two sides. Start with conformal cyclic cosmology, Penrose's beautiful idea that the heat death becomes the next Big Bang. We said that the transition works because at the end of an aeon there is nothing left but massless light, and massless light has no scale, so the cold, empty end can be rescaled into a hot, dense beginning. But think about what that requires. For the rescaling to work, everything with mass has to be gone. Every particle that carries information about what happened in the aeon, every record of every star and every world and every event has to have decayed or evaporated or been diluted to nothing. The very condition that allows the universe to begin again is the erasure of almost everything the universe ever was. The next aeon is not built from the wreckage of ours. It is built from the perfect forgetting of ours. The price of the new beginning is the complete loss of the old one. The bounce models say the same thing in a different voice. Remember cosmic forgetfulness, Bojewald's name for the fog across the bridge. The universe before the bounce is real, it happened, it gave rise to ours. But the bounce scrambles the information so thoroughly that this side cannot reconstruct that side. The previous universe is gone in every way that matters, even as it lives on through the universe it produced. And eternal inflation is no kinder. The new bubbles are not continuations of ours. They are strangers, fresh universes with their own physics and their own histories, sharing nothing with us but the empty sea they formed in. Over and over, in model after model, we find the same shape. The universe continues, but it does not remember. Continuation without continuity. Eternity without memory. I want you to feel the full weight of that, because it is one of the strangest emotional truths in all of cosmology. We tend to imagine that a cyclic universe would be comforting, that if the universe repeats, then in some sense things come back, things return, nothing is truly lost. But that is not what the physics says. The physics says that if the universe repeats, every cycle is, from the inside, the first and only time it has ever happened. The universe does not know it has done this before. There is no accumulated wisdom, no memory of past aeons, no sense of having gone around the wheel a billion times. Each universe wakes up at its Big Bang as if newborn, with no recollection of the countless universes that came before it and made it possible. The universe has died and been reborn an unlimited number of times, and it remembers none of them. And if you were somehow there, riding across the transition, neither would you. You would arrive in the new eon as blank as the universe itself, carrying nothing, knowing nothing, the slate wiped perfectly clean. There is a name for the loneliest version of this worry, and it haunts the eternal models specifically. It is called the Boltzmann brain problem, and it goes like this. We saw earlier that in a universe that lasts forever, random fluctuations will eventually produce anything that is physically possible, including ordered patches, including, given enough time, conscious observers. But here is the troubling part. A fluctuation that produces a single conscious brain, floating in the dark for a moment with a head full of false memories, is enormously more likely than a fluctuation that produces an entire orderly universe full of galaxies and history. Simpler accidents happen far more often than complex ones. So, if the universe really does last forever, and really does produce observers by fluctuation, then the overwhelming majority of all observers who ever exist would be these lonely, momentary, fluctuated brains, not real beings with real histories. Which would mean that you, right now, are far more likely to be one of those brief, accidental flickers, complete with a fabricated memory of a whole life, than to be a genuine product of cosmic evolution. It helps to understand why the simple accident is so much more likely than the grand one, because that asymmetry is the whole engine of the paradox. A fluctuation has to be paid for, in a sense, by improbability, and the more order you want, the more improbable it is, and the longer you must wait. A single brain, with just enough structure to have one fleeting moment of experience, is fantastically improbable already, but it is a small order compared to an entire universe of 100 billion galaxies, each with 100 billion stars, arranged with a history that hangs together. The full universe is so much more improbable than the lone brain that, on an infinite timeline, lone brains outnumber full universes by a margin that itself needs a tower of exponents to express. So, if observers come mainly from fluctuations, then almost every observer is a lone brain, and almost no observer is a real product of cosmic history. The arithmetic is merciless, and it is precisely that merciless arithmetic that turns the eternal universe from a comfort into a problem. Now, physicists do not actually believe you are a Boltzmann brain, but they take the problem very seriously, not as a claim about you, but as a test of theories. The cosmologist Sean Carroll put it sharply. Any model of the universe that predicts more fluctuated observers than real ones is, in his word, cognitively unstable. It undermines itself. Because if you really were a random fluctuation, you would have no reason to trust your memories, your reasoning, or the very physics you used to conclude you were a fluctuation. A theory that tells you that you cannot trust your own thoughts has sawed off the branch it was sitting on. So the Boltzmann brain problem has become a kind of filter. Models of an eternal universe have to be built carefully enough that they do not drown in fluctuated minds, and that requirement rules a lot of otherwise tempting models out. The eternal universe is allowed, but only if it does not make a mockery of the observers inside it. Human beings have circled this idea for a very long time, long before there were equations for it, and it is worth noting the oldest version, because it shows how strange the modern one really is. The philosopher Friedrich Nietzsche, in the 1880s, proposed a thought he called eternal recurrence, the idea that everything that happens has happened before and will happen again, infinitely, exactly the same, down to the smallest detail. He offered it as a test of how you live. Could you bear it, he asked, if you had to live this same life over and over forever. But notice the crucial difference between his version and the physics. Nietzsche's recurrence was the same, and that was the whole point, the same life repeating, so that what you do matters infinitely because you do it endlessly. The physics offers something colder. In the cyclic and conformal models, the universe does not repeat the same, it repeats blank. Each cycle is a fresh draw, remembering nothing, carrying nothing, and even in the Poincaré version, where exact configurations do recur, there is no thread of memory connecting them, no continuous self that experiences the repetition. The repetition is real, but no one is there to know it is a repetition. So the question of what survives turns out to be the question of what we even mean by survival. If a future fluctuation, 10 to the power of exponents years from now, assembles particles into an exact copy of you, is that you living again, or just a stranger who happens to share your shape and your false memories? If the universe begins again after the heat death, identical in its laws but blank in its history, has anything continued, or has something merely started over wearing the same clothes? These are not questions physics can answer, because they are not really about particles. They are about identity, about what makes a thing the same thing across time, and the eternal universe forces them on us with a sharpness that no candle or summer or human life ever could. So this is the real texture of no end, and it is nothing like the simple comfort we might have hoped for. Yes, the universe may go on forever. Yes, the end may be a doorway rather than a wall. But what walks through that doorway is not us, and not our universe, and not anything that remembers us or our universe. What walks through is a clean slate, a fresh start so complete that it has forgotten there was ever anything to start fresh from. Repetition, it turns out, is the loneliest kind of eternity, endless and without memory, a song that has been sung forever by a singer who each time believes it is the very first note. And once you understand that, a new and surprisingly urgent question appears, the one we have been circling all night. If all of this is happening out beyond the edges of what we can see, before our Big Bang, after our heat death, in bubbles we can never visit, then how could we ever possibly know which of these stories, if any, is true? Part 10. Could we ever know? This is the question that keeps the whole subject honest, and I have been waiting until now to ask it, because you needed to see the full sweep of the ideas before you could feel the weight of the obstacle. Every model we have discussed tonight makes its boldest claim in a place we cannot look. The cyclic models talk about before the Big Bang, and we cannot see before the Big Bang. Conformal cyclic cosmology talks about after the heat death, and we cannot wait the unfathomable time it would take to see after the heat death. Eternal inflation talks about other bubbles, and we cannot reach another bubble. The no end is always somewhere we are structurally, permanently unable to go. So the question is not idle. Can we ever actually test any of this? Or are we trapped inside a single chapter of a book whose length we can never read? Before we get to what is measurable, it is worth pausing on how unusual it is that any of this is measurable at all. For most of human history, the fate of the universe was a question for priests and poets, not for instruments. The idea that you could point a telescope at the sky and gather actual evidence about whether everything ends, and how, would have seemed absurd a few generations ago. And yet, here we are, building enormous machines whose entire purpose is to measure the behavior of the force that will decide the ending. There is something quietly magnificent in that, in a species that lives for a handful of decades, on a single world, taking the measure of eternity itself and getting real numbers back. We may not be able to answer the question yet, but we have made the question into science, and that alone is one of the strangest achievements there is. Let me start with the one piece of the puzzle that is genuinely, actively being measured right now, because it shows that the question is not hopeless. The fate of our own universe depends almost entirely on the nature of dark energy, that mysterious force pushing the expansion faster and faster. If dark energy is a true cosmological constant, unchanging forever, then we get the lonely de Sitter future, the endless expansion, the slow freeze. But if dark energy changes over time, then the future could be completely different. And here is the news that has electrified cosmology in the last couple of years. A major astronomical survey called DESI, the Dark Energy Spectroscopic Instrument, has been mapping millions of galaxies to measure how the expansion has changed across cosmic history and its results, released in 2024 and 2025, have hinted at something nobody expected. The data suggest, tentatively, that dark energy might not be constant after all. It might be weakening over time. If that is real, and I have to stress that it is still uncertain, it changes the ending. A dark energy that fades could allow gravity to reassert itself, could let the universe become dominated by matter again rather than by the relentless push of expansion. And that, in turn, reopens possibilities we thought were closed, including the possibility that the expansion could someday slow, halt, and reverse, pulling everything back together toward a collapse. The statistical strength of the DESI hint sits somewhere between roughly 3 and 4 sigma, depending on how the data are combined, which in physics is interesting but not yet decisive, the kind of signal that has, in the past, sometimes strengthened into a discovery and sometimes melted away into noise. There is real debate about whether the effect is robust or an artifact of combining datasets that do not quite agree. But the point for tonight is profound. The ending of the universe is not a settled fact in a textbook. It is an open question, and the answer is being chased right now by people pointing instruments at the sky. We are, in a real sense, measuring the fate of everything. It is worth sitting for a second with how much rides on a single quantity, because it captures the strange precision of modern cosmology. The entire future of the universe, whether it freezes, tears, or turns back to collapse, comes down largely to one number, the way the strength of dark energy behaves over time, a number physicists label with the letter W. If that number sits exactly at -1 and stays there, we freeze. If it drifts a little above -1 and weakens, the future softens and may even reverse. If it dips below -1, we tear. The whole grand fate of everything, all the stars and worlds, and the question of whether there is an end at all, balances on the behavior of a single parameter, and we are, right now, in observatories around the world, trying to measure it to one more decimal place. The ending of the universe has become, almost unbelievably, a measurement problem. There is also a second possible fate hiding in that same uncertainty, and it has a dramatic name. If dark energy does not weaken but instead strengthens, growing more powerful over time in a particularly extreme way physicists call phantom energy, then the universe ends not in a freeze, but in a tearing. This is the Big Rip, proposed in 2003 by Robert Caldwell and his colleagues. In the Big Rip, the accelerating expansion grows so violent that it begins to overpower not just the force holding galaxies together, but the forces holding everything together. First, the galaxies are torn apart, then the solar systems, then planets, then, in the final moments, atoms themselves are ripped to pieces as the expansion beats every force in nature. In the original calculation, this dramatic finale could arrive in around 22 billion years, which on the scales we have been discussing tonight is practically tomorrow. So we have, laid out before us, several genuinely different endings: the freeze, the rip, the possible turn back toward a collapse, and which one is real depends on a number we are still working to measure. But now, let me turn to the harder cases, the truly cyclic and eternal models, because that is where the obstacle becomes most severe. Can we test whether there was a universe before ours? There was, remarkably, one serious attempt. Roger Penrose, together with Vahe Gurzadyan, went looking for fingerprints of a previous aeon in the oldest light we can see, the cosmic microwave background, the faint afterglow of our own Big Bang that fills the entire sky. Penrose reasoned that in conformal cyclic cosmology, certain violent events in the previous eon, like the collisions of enormous black holes, might leave faint circular marks in that ancient light, rings of slightly unusual smoothness. And in 2010, they announced that they had found them, concentric circles in the microwave background, that they argued were scars carried over from the universe before ours. It was a thrilling claim, a direct observational hint of a previous universe, and it would have been one of the most important discoveries in history. But it did not hold up cleanly. When other researchers analyzed the same data, they found that the circles were not as statistically special as claimed, that similar patterns show up in random simulations that contain no previous eon at all, and that the apparent signal could be explained by ordinary quirks in the data and a few unusually bright spots, rather than by anything carried across from before time. Later searches for related features, the so-called Hawking points, ran into the same wall. The evidence, at best, is contested, and most cosmologists do not regard it as confirmation. The one bold attempt to see across the boundary returned a result too murky to settle anything. I should be careful and fair about the DESI result, because it is exactly the kind of finding that excites people past what the data can bear. What DESI measured is consistent with dark energy weakening, but it is not proof, and the strength of the hint depends heavily on which other datasets you fold in. Several careful analyses have argued that the apparent signal may come from tensions between those datasets rather than from any real change in dark energy, and that with cleaner data it could fade. This is how science actually works at the edge, not as a sudden revelation, but as a wavering signal that teams argue over for years before it firms up or dissolves. What is not in doubt is the stakes. If dark energy is constant, we get the endless freeze. If it weakens, the future is rewritten, possibly toward a universe that slows and turns back on itself. And that turning back deserves its own name, because it is the oldest cyclic dream of all. If the expansion ever halts and reverses, then everything that flew apart begins to fall back together. The galaxies streaming inward, the temperature rising, the universe compressing toward a fiery collapse that physicists call the Big Crunch. For most of the 20th century, the Big Crunch was the romantic favorite, the universe breathing out and then breathing back in. The discovery of accelerating expansion in 1998 seemed to rule it out and hand us the lonely freeze instead. But if dark energy is not what we think, the crunch creeps back onto the table, and with it the possibility that our collapse could become a bounce, and the bounce a new beginning, and the whole cyclic picture we have been building could turn out to describe not some exotic alternate cosmos, but our own actual future. The fate of everything hangs on the behavior of a single number, and that number is being measured imperfectly but genuinely in our own lifetimes. And this brings us to the hardest obstacle of all, the one that no clever experiment may ever overcome. From inside a single eon, from inside a single bubble, a universe that ends and a universe that has no end can look exactly the same. If you are living in one cycle of an endless chain, everything you can observe is contained within your cycle. The previous eon erased itself to give you a beginning. The next aeon lies beyond a future you cannot reach. The other bubbles are sealed away behind walls of inflating space you can never cross. Every signature of the larger, endless structure lies precisely in the regions you are forbidden to see. And so we come back to the phrase I gave you earlier, the one I asked you to remember. An ending is just an event you cannot see past. We meant it poetically then. We mean it literally now. The end of the universe, and the question of whether there is one may be permanently sealed behind the horizons of what any observer trapped inside the universe can ever measure. Not because the answer does not exist, but because we are on the wrong side of every door that would reveal it. Part 11. Does time have an end? So where does that leave us, here at the end of a story about whether there is an end? It leaves us, I think, in a more honest and more interesting place than where we started, and I want to gather it all up gently, because we have come a long way tonight. Look back at how far the ground has shifted under that opening certainty, because the distance is the whole point. We did not arrive here by abandoning science for wishful thinking. We arrived here by following the science more carefully than the comfortable summary allows, by refusing to let one small word carry 3 different meanings, by asking what the equations actually say instead of what our intuitions assume. And the more carefully we followed, the less final the ending became, until the thing we were most sure of at the start, that everything simply stops, turned out to be the one thing the physics never actually promised. That is not a failure of knowledge. It is knowledge doing its finest work, which is to take a certainty we never examined and gently, rigorously set it free. We began with a certainty. Everything ends, and so the universe ends, in a cold and final and total death, and piece by piece we took that certainty apart. We found that the death is real, but its finality was something we added ourselves. We found that even the heat death may be an asymptote. The universe approaches forever and never reaches, a last page that keeps not being the last. We found that a dead universe does not stay still, that over a long enough eternity, it twitches order back out of the dark, and sometimes, perhaps, twitches whole new universes into being. We found serious mathematical models in which the universe collides and begins again, bounces and begins again, or, most strangely, in which the coldest empty end is the very same thing as the hottest dense beginning, the end and the start written with one equation. And we found that all of this comes at a price, that the universe may go on forever but carries nothing across, remembers nothing, begins each time as if for the first time. And underneath all of it, we found a question that is even bigger than the one we started with. When we ask whether the universe ends, what are we really asking about? Because there are, as we said at the very beginning, 3 different things hiding in that one small word. There is the end of structure, the last star, and the last black hole. And that ending is real. It genuinely happens. There is the end of usable energy, the slide into maximum entropy, and that too is real, at least as something the universe forever approaches. But then there is the third thing, the one underneath, the end of time itself. And here, after everything, we have to admit that we do not know whether time has an end at all. We do not even fully know what it would mean for time to end. We can watch the things in time come and go. But whether the stage on which they come and go ever closes, whether there is a final moment after which there is no after, that may be the single hardest question in all of physics, and we have no answer to it. I keep returning, as we close, to that small word we held up to the light at the very beginning, because the whole journey has been a slow turning of it, looking at its different faces, end. We started so sure we knew what it meant, and we found that it meant at least 3 different things, and that only 2 of them are real, and that the third, the one we were most afraid of, the true and final stopping of everything, may not be in the physics at all. We added it ourselves, out of habit, out of candles and summers and grief, and when we look for it in the universe, we cannot find the place where it is written. Perhaps it is there, and simply hidden from us forever. Perhaps it is not there at all, but it is no longer the obvious, settled fact we walked in carrying. It has become a question, and a strangely open one. Maybe that is the real shape of this. Maybe the things in the universe end, the stars and the worlds and the black holes, all of them mortal, all of them passing, while the universe itself, the underlying thing, the stage and not the play, simply continues in one form or another, with no last moment, no closing curtain, no final page. The contents end. The container, perhaps, does not. Or perhaps even that distinction dissolves when you look closely enough, the way big and small dissolved in the world of the last light, and there is no clean line between the universe and the things in it at all. I told you, at the start, that there was a claim almost no one believes the first time they hear it. There is no end. You did not believe it then, and you were right not to, because belief is not what this deserves. But sit with where we have actually arrived. The end of the universe is not a fact in a textbook. It is an open question, chased by real instruments measuring real light, and surrounded by serious models in which the ending is a doorway, or an asymptote, or an illusion of perspective, or the very same place as the beginning. There is no end may not be true, but it is no longer something you can simply dismiss. It has become, instead, one of the live possibilities for the ultimate fate of everything, held open by the honest admission that we cannot yet see far enough in either direction to close it. Let me say plainly what we can and cannot claim, because honesty is the whole spirit of this. We can claim that the structures of the universe end. The stars die, the black holes evaporate, the matter dissolves, and that part of the story is as settled as anything in science. We can claim that the slide into maximum entropy is real, whether it is reached or only forever approached. What we cannot claim, in either direction, is whether the universe itself ends, whether time has a last moment, whether the heat death is a wall or a doorway. We have serious, beautiful, competing models that say it is a doorway, and we have a standard picture that treats it as a wall, and we do not yet have the means to decide between them, because the evidence lies in places no observer inside the universe can reach. That is not a failure. It is simply where the frontier currently sits, and there is a kind of dignity in naming it clearly rather than pretending to a certainty we have not earned. Sit for one last moment with how rare it is to be allowed a genuinely open question of this size. Most of the questions life hands us get answered, one way or another, and the answer closes them. But here is a question as large as any that can be asked, the question of whether anything truly ends, and it is open, really open, not because we have been lazy or incurious, but because the universe has arranged its evidence in places we may never be able to reach. There is a strange spaciousness in that, a room to breathe that a settled answer would not give you. You are allowed to wonder. You are allowed not to know. And the not knowing here is not ignorance. It is honesty. The honesty of standing at the true edge of what can be known and declining to pretend the edge is somewhere else. And so I will leave you where the physics leaves us, which is not at an answer, but at a horizon. Somewhere out beyond the last star, beyond the last black hole, beyond the cold and the dark and the long approach to a death that may never quite arrive, the universe is doing something we cannot see. It may be ending, it may be beginning. It may be that, at the scale of everything, those are not two different things. You do not have to decide tonight. You do not have to know. You can simply rest in the strange and spacious truth that the largest question there is, the question of whether anything ever truly ends, is still, quietly, open. There is no end, or there is, and from where we lie tonight, beneath our own small sky, we cannot yet see past the horizon to tell. So let the question stay open, and let yourself drift toward it, gently, with all the time in the world,